All right, so number one. Nick, will you read number one?
I hear the train coming around the bend, and as it does, I notice that it whistles seems to be getting a higher pitch. The average train whistle has a frequency of 15,000 hertz. If the train is traveling 18 meters per second towards me, what is the frequency I am?
Okay, so we've got our train. There's our train. It's coming 18 meters per second. If you know the song Folsom Prison Blues, you know this, I hear a train coming around the bend?
No.
Anyway, if you did, then that'd be you in jail, hearing the train coming. Okay, so there we go. Coming towards you, you're in jail, and you notice the frequency's a little high. Traditional train whistles, it's stated, we assume that the original frequency is 15,000 hertz, and we expect to see or hear a different frequency. What's the rule or the theory that affects why we hear a different, what's it called? Why we hear a different frequency? Doppler effect. All right, so the Doppler effect equation says that the new frequency will equal the original frequency times the velocity of sound plus or minus the velocity of the observer over the velocity of sound minus or plus the velocity of the source. Okay. And so we start out, this is important to understand whether you have the original frequency or the affected frequency. It says that a standard train whistle or an average train whistle has a 15,000 hertz sound. So we're assuming that that's the original actual whistle, not what we're hearing. But on the test or anywhere else, you could come across a problem where you're trying to figure out what the original was given what you're hearing. So in this case, we are looking for f prime. It equals 15,000 times. Now we've got to figure out what the velocity of sound is. Most trains operate in the air. You know, not flying in the air, but in the air. So we assume the velocity of sound is going to be in the air. It's 343 meters per second. If it was somewhere else, the speeds of sound are listed in the textbook. I don't remember exactly where, but you'll find it. It's in the book. Plus or minus, how fast is the observer moving? That guy up there, he's in jail. He's not going anywhere. So 0. And then this is minus or plus, how fast is the source of the sound moving? It's moving 18. Now we have to decide whether we're going to use the top sign or the bottom sign. The way we usually do this is we determine, do we expect the frequency to go up or down as the train approaches? Up. And because the frequency is going to go up, we're going to use the upper sign and reject the lower ones. Well, 343 plus 0 is just 343. So this becomes 15,000 times 343 over 343 minus that would be 325. And if we calculate that through in our calculator, 15,000, is it 380? 830. There you go, 830. Now, obviously, for sig figs, if I looked at the problem, I think I'd go to just, is it 2 sig figs? I've only given the 2 values. So that would be 16,000 hertz. I'm okay with either one of those. Remember, I'm not going to grade your sig figs, but if you're in the habit of using them, you probably should just stay with that habit. That's a good habit to have. Any questions on question number 1? Okay. Question number 2 is an example of the kind of thing that I might put on the test. It won't necessarily be this question, but I could definitely see myself finding a place for this. And honestly, if it wasn't so hard to grade your writing, I would probably do the whole test this way, because it's a really good way for me to figure out, do you know what in the world's going on? Literally, in what in the world? All right, anyway. It says Kate is going to start a tuning fork only band. He has a few unlabeled forks and wants to determine what the frequency is for each of them. Using only the tuning forks and his ears, how could he ever figure out what the frequencies are? And so this is about you explaining a process. So I'm just going to kind of basically walk you through in a really simple way, and I expect whenever I come up with a question like this, that you just use words to reason through what you would do or how you would approach something. So let's just imagine I've got some different tuning forks here. let's say I have one that I don't know. Let's say I have one at 316 hertz and one over here at 320 hertz. When I play these two together, I hear a wobble, or what we call a beat frequency. Let's say that I hear 3 beats every second, okay? Per second. That means, based on our beat frequency rule, that it's 316 plus or minus our 3, meaning it's either 313 hertz or 319 hertz, okay? Just by playing those two forks together and hearing the 3 wobbles per second, I can determine it's either 313 or 319. But I don't know which unless I use another tuning fork. And so this is that explanation of, well, you'd have to do this. And then you would want to go and do this. So you'd be explaining the whole process. Now if I did these two together, and let's say that I had 7 beats per second, or 7 hertz for a beat frequency, that would mean that it's either 313 or 327. Now, what would the unknown frequency have to be? It'd have to be 313 because it's the only one that answers both with the same answer. Okay, so how would we describe that in our own words? Well, I'm sure that would include a paragraph, and you'd be explaining along the way how that would go. Okay,
but we didn't have any numbers to begin out with, so why did we just make that?
This was me giving you an example of how I would explain it. You could use numbers in an example of explaining, like, say for instance, I had this number. This is what I would do with it to find what I needed. See, I want to know if I take away numbers, can you still explain your way through the concept of the physics? Or are you someone who legitimately has to be given 3 out of 4 variables from a formula and solve algebraically? Are you essentially a glorified mathematician, or are you a physics student? Because a glorified mathematician, I can hand my Algebra 2 kids most of these equations, give them 3 variables, they know nothing about what's going on, but they could plug the numbers in and solve. I hope that you can explain some of what's going on. Okay, that's what I really want to know. Can you explain what's happening? All right, so there's question number 2. Anything before we leave question 2? Obviously, question 2 would be a paragraph type answer, a few sentences. All right, number 3. So we keep going. So I've got a dog that barks at night just up the road from my house. If my new earplugs promise to block out any sound with a sound level less than 80 decibels, okay, the question is, the dog's barking is set at an intensity of 70 watts per meter squared. Will the earplugs block out the sound? So here's the issue. I have 80 dB earplugs. I'm missing a 0 there. 80 dB earplugs and 70 watts per meter squared. This is an intensity. This is a sound level. I cannot compare them directly. I have to either turn both of them into intensities or both of them into sound levels to be able to compare what's louder, the dog bark or my earplugs blocking out the sound. Which one's going to do better? If the dog's bark is above 80 decibels, I'm going to hear the dog. If the dog's bark is less than 80 decibels, I won't hear the dog. That's the whole concept of the earplugs. So I can either turn my intensity into sound level or my sound level into intensity. Traditionally, just because it's the traditional formula, I'm going to try to turn this into a sound level. And so the formula for beta is 10 log of I, which would be 70, over 10 to the negative 12. It's always 10 to the negative 12 in the denominator there, but it's important that when you type it in your calculator, you would put E, you put 1e negative 12, not 10e negative 12. It'll make you off by a factor of 10, which is a bad thing. If I just type this into my calculator, just the way it is, beta, I believe, comes out at around 138.
Wait, you said the 10 to the negative 12 is 1e negative 12?
Yeah, because the E stands for 10 to the, and so you'd have to do like a 1 times 10 to the negative 12. So it'd be 1e negative 12, if you were going to type it in with scientific notation. You could just type 10 raised to the negative 12 in parentheses, and it would work there too. Is it about 138? 0.45. Decibels. All right. So the question is, will I still hear the dog? Now the dog is way bigger than the 80 decibels that the earplugs are promising to knock off. Now maybe it'll still make the dog a little quieter. Maybe I could sleep through the dog's loudness now. But just so we're clear, 140 is crazy loud. Okay? Crazy loud. Like rock concert loud. So this dog is clearly the result of some sort of genetic experiment.
It's like the dog off the Sandlot.
Yeah, dog off Sandlot. It's the beast. Like, terrifying animal. Okay, if your dog's that loud, you need to move away from me.
Something like 120 decibels, the basis for like hurting your ears.
Yeah, so 120 is the threshold of pain. 140 is like a jet engine when you're standing about 30 meters away or something like that, but not too far away. It's loud, crazy loud.
So would that cancel out 80 decibels, or and you'd only hear?
It depends on what they're doing. Probably it would be similar to that, but it also would potentially cut even more, just depending on how the intensity travels. But you got to be really close to this dog too, so I don't know how close you have to be. It's an unrealistic problem because there's no way the dog's that loud. But I just throw numbers at you sometimes. Now, question number 4 is a ray diagram. I'm going to do all the ray diagrams in a second video, okay? So skip 4 for now. We'll come back to it. It'll get covered when we do, because there's 4 different types, so I want to do all 4 types. So if we go over to question number 5, we have an air to water deal. And we have a ray of light coming in and then bending. We have our perpendicular here. This is 40 degrees, and I want theta 2 right there. All right, so how are we going to start this? What rule drives the bending of light? It's called Snell's law. It says N1 sine of theta 1 equals N2 sine of theta 2. N is the index of refraction for different materials. If you don't know them, they are in the book under index of refraction, indices of refraction, I guess. What is the N value for air? 1 times sine of, what's theta 1?
40.
If you said 40, I gotcha. It's always measured against the perpendicular. I'm not promising to try and mess with you, but I'm probably going to try to mess with you in some way, shape, or form. This is 50. That's theta 1. Equals, what is the N value for water? It is 1.33 sine of theta 2. Now, could I ask you for this angle over here? I could, right? But would this formula give you that angle directly? No. We subtract from 90 just like we did earlier in the problem. So don't be afraid to just go through the process and then go back and look at the question. But I'll divide by 1.33, and then I'm going to take a sine inverse. And theta 2 comes out to
35.
roughly 35 degrees. Any questions? Okay, so now what we're going to do is go to question number 6, where we have the polarizers. Okay, we have the sun. Okay, shining. We have a polarizer followed by 2 polarizers that have been shifted how much? Each time 15 degrees past the other one. So And the question is, how much light gets through? So we're going to actually just try to calculate the percentage or portion of the light that gets through. So we're going to call this I naught. And we want to know what decimal of that I naught comes out. So what's the rule for the first polarizer?
1/2 I naught.
1/2 gets through. Through the next polarizer, how do we get the second value? 1/2 I naught
Sine.
cosine squared of 15. Okay, that's what goes right there. As I go through another polarizer that's shifted another 15 degrees, what do I do now?
Squared.
Same thing, 1/2 I naught cosine squared of 15 times cosine squared of 15. Every time I go through another polarizer, I multiply by that cosine squared of that angle of rotation. If I had a 25 at the end, another 25, I would times by the cosine squared of 25. I just keep going as I went. Okay. This right here will have my answer in terms of I naught. It'll be I naught times some number. The issue most people have is how do you calculate 1/2 cosine of 15 squared times cosine of 15 squared. People struggle a little bit with the calculator. So what I'm going to do, I'm going to try to make this really simple by just showing you how I would type it in. First thing I would do is do the cosine of 15. Now as long as you're in degree mode, you'll get 0.9659. I need that squared. Okay? That right there is cosine of 15 squared, correct? We squared the cosine of 15. I want to multiply the cosine squared times itself, correct? Which means to do what?
Square.
So I'm going to square my answer again. That gives me all the cosine squares have been managed. I need to times that by 0.5 to get 0.435. 0.435 of the initial light gets through. So 44% of the initial light is going to get through. Okay. As a side note, if the angle is the same the whole way, we just keep multiplying by the same value over and over again, right? Be careful. If the angles are not all identical, you have to make sure that you multiply by the cosine squared of that angle, then the cosine squared of whatever the next angle is. Be careful that you do it correctly that way. Are we good? If I threw 10 more polarizers on there, would it change the problem very much?
Not really.
No. You just
have
keep
to
doing
do
it.
it 10 more times, right?
Yeah.
Or
Alright.
could you just raise it to the 9th?
So that's actually a really interesting question. Let's talk about it real quick. If the angle is the same, okay, so this is a big if. If the angle is the same, you have 1/2 I naught cosine squared of theta. But that cosine squared of theta keeps getting multiplied over and over again, right? So we could say it's exponential in nature. How many times did I use it on this problem up here?
9 times, or raise
No.
it twice.
Just use it twice. But how many polarizers were there?
3,
If there were 10 polarizers, how many times would I use it?
9.
So it's never the number of polarizers, it's always one less, right?
Yeah.
So we could say this is to the n minus 1. This right here is an equation that will work for every problem where the polarizer shift is always the same amount. If I change any of the angles, it falls apart. So be careful. I haven't written the test yet, so I don't know what I'm going to end up doing. But if it was 7 of these, and they were all shifted by 15 degrees, you could literally just put a 7 there, type the whole thing in the calculator the way it looks, and be just fine. So that is an option. All right. Question number 7. Oh my goodness. All right, number 7. We have my daughter and some boy that I don't trust. I'm trying to keep them apart. She is such a positive, wonderful person that she has a charge of 5e,
Yes.
and actually, you know what? He's got like a nose ring or something, and a beard. That's not good.
How old's your daughter?
That's the problem. 9. All right, so
That's a boy.
yeah.
Wait, so is this like a real thing that happened?
no,
What? No.
no,
No, not.
it's
Of
not.
course, not the old guy, but like
No,
a
no,
kid. in
no.
grade or
But
something.
I've said for a long time that my becoming a high school math teacher is part of a 30-year plan to control my children's lives. They don't know it. Like, it's going to seem like, oh, well, you're just a teacher, so of course you're at the high school. But really, I'm just here to make sure that I like what happens. That's all.
All fair.
Yeah, that's all.
That's
Anyway.
funny. You thought ahead, man.
So I've got a positive 5e, I've got a negative 3e. The question is, if they are 0.062 meters apart, okay, how much force do I have to apply to keep them apart? Now, obviously, the person, another person, like, that's all just nonsense. This is really about charges being attracted or repulsed, and that's part of what law? Or whose law? Coulomb's law. Coulomb's law says the force between any two charged particles is K Q1 Q2 over R squared. K is a constant, that's good. 8.988 E9 times, now the Q, the charge of my daughter's particle, if you will, was 5e. What does the E represent? Not the E on your calculator. It's an electron's charge.
Wait, 119.
No. So I'm going to do 5 times 1.602 E negative 19. That's 5E. But I also have to multiply by the boy's charge. Now, it says negative 3E. It does not matter if you leave it negative or not when we're deciding the value of the force. Because if it's negative, it just means that they're being attracted. If it's positive, it means they're being repulsed. And so my force would have to counteract that. Direction isn't going to matter. So I'm just going to put a 3. Feel free to put a negative 3. It doesn't matter. 1.602 E negative 19 again. All of that gets divided by 0.062. I'm going to rewrite that. 0.062. Square.
8.988 E, and that's a constant.
Yep, this is K. It's a constant, never changes. The Q's are there for you to cipher your way through and figure out what they are. This is going to come out very small because charged particles, while they are attracted to each other, at that distance, it's really hard to get them. You look at that E negative 19 on the numerator twice. It should come out pretty small.
Is 0.062 squared on the bottom.
0.062 squared on the bottom. That's the radius or the distance between them. And
Couldn't we do 1.602 E negative 19 squared times
you could.
15?
Yeah, you could do a 15 from those, and this could be squared because it's repeated. So it's just a matter of how you type it in the calculator and your approach. If you get it right, 9.0 E negative 25. And that would be in newtons because this is a question about forces. We're killing it.
Wait, would I square on that side of the parentheses?
You have to make sure you're only squaring the E negative, the 1.602. So if the 1.602 E negative 19 is in its own parentheses, yes. If it's part of a bigger parentheses, no.
Oh yeah, it's in its own.
Yeah, then I would square after the parentheses.
Okay.
Okay, we're on to 8, right? So I got a light bulb in my house. I don't know how many watts it uses, how energy efficient it is, because it's not labeled. But did you guys get the joke? What does a nearly deaf electrician say when he can't hear you? What's that?
What did you just say?
No, he sees your lips moving.
Oh,
Yeah.
No, he's not blind. Give him
How
credit.
inconsiderate of you.
okay.
Don't judge him. All right. Question number 8. I'm asking for the wattage, and I also ask for what current flows. What does wattage measure? It measures the power. So I'm asking you for power, and I ask for what current flows. What value is measured as current? What variable?
Amperage.
Amperage is its unit. What's its variable in equations? I. I thought you were going to say I don't know there for a second.
I don't want to get it wrong.
So we're asked to find the power and the current, P and I, and we're given what information?
Resistance and volts.
So resistance is it 5200?
520.
520, okay.
You use Ohm's law.
So there's that, and then 110 volts for V. And Mitchell said we're going to use Ohm's law. And if you leave this room at the end of the year and you don't understand the structure of Ohm's law, I don't care what grade you have in the class, you failed. Like you just didn't take advantage of the opportunity you were given to learn something. Because this is fundamental to everything that we do with electricity. You cannot do anything safely with electricity without understanding that principle right there. So the voltage is 110. The current is, I don't know. And the resistance is 520. We just simply divide our current, comes out to be 0.211. 212. Okay, 0.212 amps. Depending on how you want to do sig figs, there's your current. Yeah, Cash?
You answered my question.
All right, very good. And then to find power, how am I going to find power? I can use P equals IV. And if you don't like using I because it's a rounded value, use the whole thing in your calculator. Or I is technically, if you change this over, bring the R over, it'd be V over R. So there are other versions of this equation that you could use if you wanted to avoid using rounded values. That's all up to you. On a test question like this, it's not going to matter. But in the long run, like if I was going to be an electrician, obviously rounding could be a little bit of an issue. You always give yourself lots of room for tolerances. So if I did just P equals IV, it's 0.212, or whatever values in your calculator, times the 110. And what is the power for our light bulb?
23.3.
23.3?
Well, it was 2.6.
All right, so 23 watts, basically. Thank you very much. Okay, and so 8 is all about finding these individual values, power and current, but we're really talking about Ohm's law and then the power rule. P equals IV and V equals IR. When we get to number 9, we're being asked to find how much charge something is. So charge, how do we measure charge, or what's the variable for charge? I mean, that's one of those things where I ask you for charge. If you don't know what you're even looking for, you can't even begin to look for formulas or structures that would help you solve. So what variable represents charge? Q does. And it can be big Q or little q. What unit does it use?
Isn't it?
Coulombs,
Yeah.
which is confusing because it's a big C, but that's a Q. Okay, but then I say there's 13.5 microfarads. The micro is E negative 6, but what's a farad represented by in an equation?
Resistance.
C. Resistance would be in ohms.
This is everything that's confusing.
This is the part that gets a little confusing because the variables represents units, and variables, they're different. So this is C an equation measured in farads. Okay, that's why the F is there. And then what's the other value you're given? Voltage. 13 volts is obviously a V in an equation. It represents volts, right? Okay, so those are our units across the bottom. This is the variables. and then up top is what we're asked for or given. Okay. Is there a relationship between Q, C, and V? Yeah. It's actually Q equals CV. Okay. Well, I just need to multiply those two things together. The Q will equal, what is 13.5 e negative 6 times 13?
1.755 e negative 4.
So let's go 1.76 e negative 4. And what do we say its unit would be?
Coulombs.
Capital C for coulombs. So this question, it's not a hard question, and I could change it up a little bit, but really it's not going to be a complicated problem. Where you're going to have issues is more with regards to, do you understand what unit goes with what variable and what variable goes with what request? If I asked you for what's the capacitance, what capacitance is necessary to put this much charge on a circuit with this voltage supply, you'd be looking for the C in the equation. Okay, so you got to just be careful you understand how to interpret what's there. All right, we're practically done. So only 12 questions. We're on 10. 10 is a piece of cake, like 3B. What does that mean? It's probably not even going to be on the final because it's so easy. All right, what amount of resistance? Okay.
Is in a circuit with a voltage of 86.
We have a voltage of 86 volts.
Current is 1.5 milliamps.
1.5 milliamps.
So is that 9 or 6?
This is number 9. Wait.
No, million.
Milli is E negative 3.
Oh,
E negative 6 is micro.
okay.
Milli, think about it. How many milli is 1,000, right?
Yeah.
But millis are small, aren't they? So it has to be less. So it's got to be negative. All right. So if we go through, this is just Ohm's law. This is what I mean by it's too easy. V equals IR. So 86 equals 1.5 E negative 3 times R. And if we solve for R by division, I think it's 57,333.
Yeah, 0.3
We use that Greek letter omega for ohms. Hey, isn't that kind of convenient that his name was Ohm and that, like the Greek letter omega, like it's just, if you have the right kind of name, it just fits really good. So, well, there you go. 11 is probably one of the most challenging questions just because of the layers that I put into it. It's really not that hard, but I put a lot of layers into the problem. Okay. All right. Help me draw this. And guys, I'm going to forewarn you. If I were doing this, I would probably redraw this circuit about 5 times, and I'll do that up here on the board. But on your own paper, you're probably going to want to redraw it. Are we good so far? I'm coming down, turn the corner, and split to a single over a double with that there to that. Well, I'll make this straight here. Okay, so that should look like yours, right? All right, and then the numbers are 3, 2, 4, 3, and then up here's 5,
And then
1, 5, 2. Okay, and that one's 4. Okay, if things are in series, connected directly, we just add them up, right? So we want to do any of that kind of stuff that we can do right away. I see it here. I also see it right here. Okay, those are not parallel to anything. They're just directly in series, so I can combine them. That's going to make my picture look this way. 7 splits to 6 and 3, right? Down to I still have my 5, 1, 5, and 2. Do you see how I'm saying I'm going to simplify, just redraw it? Take parts of it out? Probably going to do this at least once, if not twice more. Okay, how do I combine the 6 and the 3?
1 over.
It's the 1 over. So this right here is 1 over 6 plus 1 over 3 to the negative 1. Someone want to take their calculator and check that real quick? Turns out to just be 2. Okay. So this right here became that. Instead of having that parallel chunk, I just put the 2 there. All right, now here, this is where things get a little more complicated. In this bottom part, where do I need to start?
I started at 1 and 5.
Yeah, this thing right here is the most layered. It's the parallel inside the series inside the parallel. It's the most, think about sets of parentheses, it's the most layered. So this right here is going to be 1 over 1 plus 1 over 5 to the negative 1. You can imagine seeing all of that. And so I come down here, turn the corner, go up. I've still got my 5. But now I've got 1 there, and then my 2 there. Okay, so what did this guy turn out to be? 0.833. Yep. That's what that guy was. And he used to be up here. That was the 1 and the 5 combined. So I'm redrawing it so I can simplify my life along the way. We okay so far? I'm going to draw it over here now. The 7 and the 2, can I just combine those?
Yeah.
All right, so I'm going to make that a 9. 9. Now when I come down here, I still have my 5 here. But is there a way to replace and just put 1 value for the 2 of these guys? Right, we're going to just straight add those. That's 2.833. Let me ask you a question. If I'd started with this diagram that you have right now, it's an easy question, right?
Yeah.
So it's about doing a piece at a time. This is the how do you eat an elephant question. You've heard that, right? One piece at a time.
Yeah.
Not just, I've never eaten an elephant, so I just trust the saying. Anyway,
What about Sears?
what do we do about this? This is the 1 over 5 plus 1 over 2.833 to the negative 1. And while I'm at it, I'm just going to add 9 because I know I can just straight add the series piece. This will just spit out my final answer. Now I could have redrawn it again if I'd wanted to. I could calculate these individual pieces on their own. But where are we? 10.8 ohms, or roughly 11. Whichever way you want to write that. Questions?
Oh, that's right.
Okay, so I'm going to make a little caveat for those of you who are only watching the video. The next question is something that happens in three-dimensional space. It's not going to make sense just looking at a board or a computer screen. So be aware. All right. Question number 12 is about the right-hand rule. We have person space up here, and we have a bunch of x's. I've got an electron gun. You have to make electron guns and stuff look kind of childish because you're not allowed guns in school. You always make them into bubble glowing guns. Yeah, I said it was an electron gun, right? So it's going to take an electron and send it this way. Question is, will it be turned to come hit him in the nose? That's the question. And your answer is a yes or a no, but really you should show me what's going to happen. So the right-hand rule says, first, we put our fingers, you can imagine,
In the direction of the arrow.
in the direction of the arrow. There's my short, stubby fingers. And then I am going to curl them to match the magnetic field. These x's represent the magnetic field. What does the x mean? It means into the sheet of paper or board or screen that you're looking at. Now, which hand do you have to use, Maya? The right hand rule. Okay? Just making sure you're okay. So I have my hand, fingers pointed to the right. Then I have to curl them into the board. Okay, so into the board. I don't know how you draw into the board in a two-dimensional surface. But imagine those curled towards the x's, down into the page. Which way would my thumb be pointed? My thumb would be right up here. So what does that mean? It would hit him in the face if it's a positively charged particle.
It's not.
This is the direction that positives would move, but I have a negative, so mine would go down, and I would say no. Okay? The right-hand rule is a process that if you don't understand it, the question's going to just be hard.
Wait, is it the proton and the electron? Just because it's positive, it goes up, and because it's negative, it goes down?
Positive follows your thumb, negative does the opposite of your thumb.
Okay.
All right?